Hello, I tried to quickly put this together on Friday morning before I left for vacation, so apologies if this ends up being a little rushed or incomplete. But basically, we have a grid, a 16 seed tournament bracket, and we want to know what is the hardest position to be in, where hardest is essentially going to be defined by the product of the seeds in that you might face. And it's actually the geometric average, but taking, nth root of something doesn't change the order of things. So I'm going to talk about things in terms of the product, even though the question says the geometric average. And the lower that product is, the harder supposedly it's going to be. And importantly, we're going to assume that the lower seed team, as long as you're not in the game, like the seed that you're worrying about, as long as they're not in the game, we're going to assume the lower seed wins. So it's the hardest potential matchup you might end up facing. And so the first thing I'm going to do is kind of fill in this grid with all the potential winners, the kind of worst case scenario winners, the lower seed winners that would make your trip down this path the hardest that would possibly be. Importantly, I'm not putting anything in the champions bucket because in the champions bucket should be you, right? Whatever seed you're analyzing, I guess we're only presuming you get to the final game. I guess we don't actually assume we have to win, but we're thinking about what's the hardest path to victory here. So, two things to note here is certainly we're not going to be in one of the lower seeds, so 1 to 8. And why is that? Well, it's because in any bracket we might start in, it's clearly harder to be the 15 seed than the 2 seed because the 15 seed plays the 2 seed and everything else plays out exactly the same. And the second seed plays the 15 seed, which is a much bigger number, so it's going to have a higher product. So for wherever we start, we're going to end up in the worst seed, the bigger seed, the supposedly less good seed in this bracket. The other thing to notice is that for every kind of pair of brackets at the end, it actually doesn't matter which one you start in. So why is that? So let's start at the top. 16 and 9 actually have the exact same kind of product, the same difficulty of execution of winning the thing, because they end up playing the exact same teams, right? So if you start at 16, you play 1 first, and then you get to the second game and you're going to play 8. Whereas if you start at 9, you play 8 first, and in the second game you play 1. So it doesn't actually matter where you start between those two positions. You're going to end up having the same path. And then to figure out what the rest of the path is going to be, it's going to be, well, if I'm 16, I play 1 here, I move to here, I play 8, I move here, I play 4, I move here, I play 2. So in the 16 seed, which intuitively you think, oh, well, the 16 seed surely has the hardest path. That actually isn't quite true because they play 1 right away. And then from there, it's actually one of the easier paths. After 1, they play 8, then 4, then 2. Whereas compare that to something like seed 14, which actually ends up being one of the two hardest positions. I start with 3, right? So I play 3, then I play 6, then I play 2, then I play 1. So the total seeds I'm playing are 1, 2, 3, and 6, and I'm comparing that to 1, 2, 4, and 8, where 1, 2, 4, and 8 are generally bigger numbers than 1, 2, 3, and 6. So the 1, 2, 3, 6 path is going to be harder. So you could just go down each path, and for the general question, that's fine. And it turns out that the optimal path, or not optimal, I guess the opposite of optimal path, the hardest path through this bracket is starting at either 14 or 11. In either case, you're going to end up playing 1, 2, 3, and 6. And that path, from a difficulty standpoint, the difficulty is strictly higher than almost every other path. The only path that you might otherwise consider is the path where you start as the 12 or 13 seed, where if you're the 12 or 13 seed, you end up playing teams 1, 2, 4, and 5. So what do I mean by strictly dominates? I mean the 1, 2, 3, 6 path. Well, 1, 2, and 3, I mean, those are the lowest numbers you could possibly face. The only thing that makes it a little bit easier is that you have that 6 seed somewhere in there. And so if you have another path that say, 1, 2, 4, 8, well, 4 is higher than 3 and 8 is higher than 6. So clearly the 1, 2, 3, 6 path is going to be harder. Well, there's another path that could do 1, 2, 3, and 7. That's also going to be harder. The only path that has a number less than 6 in it is this 1, 2, 4, 5 path that I mentioned before. And then the question is, well, which is harder according to the criteria of the puzzle, 4 and 5 or 3 and 6? Because those are the two differences. Well, 4 times 5 is 20, 3 times 6 is 18. 18 is lower, so that's considered the harder difficulty for the purposes of the puzzle. And this is going to be useful later, but as a general rule, if you have two numbers that add up to the same thing, in this case 4 and 5 and 3 and 6, both add up to 9, then the way to kind of maximize that is to have those numbers as close together as possible. So in general, 4 and 5 is going to have a higher product than 3 and 6, and in general, not specifically 4 and 5 versus 3 and 6. And in general, the closer those numbers are together, the higher the product's going to be, and therefore the easier, according to the game, the path is going to be. And so in this case, we're going to do 1, 2, 3, 6. That's going to be the hardest path, and that happens at seeds 14 and 11. Now, for the extra credit, which asks, okay, consider this fraction, which is, I have these two optimal seeds here, 11 and 14. Consider that as a fraction of the total number of teams in the tournament, which is 16, and take the number of rounds to infinity, basically. So, right, we have one round here versus where 1 and 2 play. We'd have 2 rounds if we get up to 4 teams. We have 3 rounds if we get up to 8 teams, right, et cetera, et cetera. And so as you make the number of teams larger and larger, it's going to be some, 2 to the n for some n. As n gets really big, what is that fraction? Meaning, in this case, it's 14 over 16, 11, 16. What is that fraction going to converge to as n goes to infinity? So there are 2 things we need to do to set up before we start solving this problem. The first is figure out, well, what's kind of my optimal path? I'm going to make a claim here. I'm going to do this a little bit sloppily again, kind of for time. I'm trying to do this in like an hour in the morning. So it's going to be a little bit sloppier than usual. But my claim is that the optimal path has, you're going to be fighting or, playing against teams that follow this pattern where it goes 1, 2, 3, 6, 11, 22. What is this pattern? Right, so I have the sequence AI, and I'm going to go back to the bracket for a second and say, well, what is this 1, 2, 3, 6, 11? So that's, we're facing team 1 at the end, we're facing team 2 here, we're facing team 3 here, 6 here, and as we move on, we're eventually going to go to 11, which happens to be what 6 plays. And basically the sequence is going to be figure out who the team that's last in the sequence, figure out who they play in the previous bracket, and that's going to be the next team in the sequence. So that's my claim. So why do I think that's true? So first, let's think about how the bracket gets made. Basically, as we go, as this bracket gets extended one round at a time, you'll notice that if I ignore the left side here, this is just what the 8, and ignore the possible winners here. This 1, 8, 5, 4, 3, 6, 7, 2. This is what the 8-team bracket would look like when it's set up. And basically to go from the 8-team bracket to the 16-team bracket, what I'm going to do is take all those individual players and separate them. So 1 gets its own game, 8 gets its own game, etc. I'm going to seed them against the team so that every single game has a total seed sum of 17. 17 is just the total number of teams plus 1. So 1 faces 16, that adds up to 17. 8's going to face 9, that's 17. 5 is going to face 12, that's 17, etc., etc. And that pattern persists for every stage of the bracket. So my claim is, because that's the way this gets seeded, my claim is that so I'm going to break this down to what I call the primary seed and then the alternate seed. And so what do I mean by that? I'm going to call 11 the primary seed in our game, where it's going to be the lower of the two optimal seeds. So 2 seeds at any stage, 2 seeds are going to have the hardest path, and I'm going to call the lower seed the primary one and the higher seed the alternate one. And it's the primary seed that we're going to follow along to figure out how this path goes. And so my claim is, right, if the hardest path is, in the 8-team game, if the hardest path is team 6 or 7, 6 is going to be my primary seed, 7 is going to be my alternate seed. And to figure out what the next hardest path is, I'm going to take that primary seed and continue on and see who 6 plays in the round previous. So in this case, 6 is going to play 11, so 11 is going to be the new primary seed. So why does that work? Well, suppose I wanted to deviate, right? So in this case, 1, 2, so we're going to go, I guess, 1 further back because it's kind of obvious that the 6 seed is optimal in the 1, 2, 3 setting. So let's go back. Let's go to the round of 32 and see what it looks like there. So in the round of 32, 11, well, what's 32 plus 1 is 33. So 11 is going to face the 22 seed. So why do I think 22 is going to be one of the optimal seeds? Well, let's suppose I wanted to deviate from that, right? Instead of 22, let's say I wanted to go somewhere down here, because 7 is going to face not 22 but 21. So maybe 21. Well, it's not going to work. That's actually not what's relevant. What's relevant is that seven plays 10 and 6 plays 11. So if I pick 22, then I'm going to play 11 and then I'm going to play 6. And I might think, well, can I do a little better if I play 7 and 10 instead of 11 and 6? And the answer is no, because just like before, when we were comparing 4 and 5 versus 3 and 6, right? 7 times 10 is 70, 11 times 6 is 66. That's the lower product. The further apart these numbers are, given that their sum is the same, the product is going to be lower. So I can't do better by doing a little deviation and fighting and playing against 10 and 7 versus 6 and 11, because this product is already the kind of more extended one. And if I say I should like 215, I mean, things get a little bit more complicated there, because now basically what I'm doing is I'm replacing, and the way to think about it is I'm replacing what I already know to be optimal with something worse, right? I'm essentially replacing 3 and 6 with 2 and 7, and then I'm taking 15 instead of a lower number like 11. So it just doesn't work to do any deviations like that. It similarly doesn't work to do deviations up here. You might think, well, 4 and 5 is worse than 3 and 6, but 4 and 5 are lower numbers than 6. But the problem is that they're higher numbers than 3. So whichever way you go, if you try to go against, say, whatever the 13 seed is playing, that 13 seed is going to play a lower number than the 11 seed. So it might be harder from that sense. But the product, right, 13 plus whatever number gets it up to 33, I guess 20, right? 13 times 20 is going to have a worse product than 11 times 22. I guess I did the math wrong. Because we're trying to get to 33. Yeah, no, that's right. Well, yeah, 13 times 20 versus 11 times 22, right? 13 times 20 is going to have a higher product and therefore an easier time than 11 times 22. So there's no point in deviating from the strategy. So the primary seed is just going to continue on. And so the sequence is take the seed that they play the round previous, and that's your new primary seed. And so our sequence goes something like 1, 2, 3, 6, 11, 22, and so on and so forth. And so I have the sequence AI. How do I get the next number in the sequence? Well, first I'm going to define 2 to the I as the number of teams at any point in the sequence. And so if I want to go from AI to the next number in the sequence, which is AI plus 1, what I do is take the number of teams in the bigger sequence, so that's 2 to the I plus 1. That's the number of teams in like the next stage of the tournament. Add 1, because that's what our seed sum is going to be, and subtract out what I start with. So that's the next number in the sequence. So as an example, if I want to go from 6 to 11, 2 to the I plus 1 is 16, right? In the 6 is the optimal number, or the primary seed, I'll call it, in the 8-team game. So 2 to the I would be 8, 2 to the I plus 1 would be 16, add 1 to it, because the seed sum is going to be 1 more than that, subtract our original 6, and we end up with 11. And so this is going to work for any possible way to do it. Where is this going to converge? This is probably the hardest part of this problem. And so what I want to know is what, and by this, I mean AI over 2 to the I. This is the fraction I care about. It's the seed number, the primary seed, divided by the number of teams in the tournament. And where does that number converge? Well, what I know is that if I go to the next number in the sequence, right, and divide that by 2 to the I plus 1, they should converge. In other words, the left number and the right number, as I gets bigger, these numbers should get closer and closer and closer together. And here, I could have had another stage that said, a to the I plus 1, but I'm just replacing a to the I plus 1 with what I've already shown you in where AI goes. So this term in the numerator here is a to the I plus 1. So where does that go? Well, I'm going to do a little bit of simplification. I'm going to cancel out the 2 to the I plus 1s, and that ratio is 1. Then I'm left with 1 minus a over 2 to the I plus 1. And this is where it's a little bit sloppy. If I had more time, I might do a stronger mathy proof, but the underlying intuition is correct here. I can kind of move some things around, right? And so AI, I'm just multiplying everything by 2 to the I essentially here. AI is essentially converging. These two numbers are getting closer and closer together as I goes to, or that's actually not quite right because these numbers might get further apart by scale, but we're going to ignore that. Um, and now I'm going to go back to and dividing this by 2 to the I. Why am I going to do that? Well, basically, what I'm going to do first is take these a to the I over 2. I don't know. For me, it's just easier to do it here than it is to do it up here, although I could do it up here with these 2 to the I fractions as well. And this is a bit more kind of realistic. This AI over 2 to the I is going to converge to 2/3 plus this term, which goes to 0 as I goes to infinity. So the important ratio here is 2/3, right? That's going to be the fraction that the primary seed converges to. Now my question is, well, I have this primary seed, but what about the alternate seed? And it turns out that number also converges. And so I want to figure out what's the fraction of the alternate seed as a function of the primary seed, or as a function of anything, I guess. And so in terms of the example, right, 14 is our alternate seed versus the 11 primary seed that we had before. So how do we go from 11 to 14, or in general, from the primary seed to the alternate seed? Well, I take my AI, the number in the sequence, which in our example was 11, and I'm going to actually go backwards through that same process. So to go backwards, I figure out, well, if I'm going to go 2 to the I plus 1, that's the number of seeds. I'm going to figure out who team 11 is playing. So in this example, right, 2 to the I is 16, plus 1, there's 17, minus 11, that's 6. So 6 is both the team that 11 plays in the first round of the tournament and the previous primary seed. Those are the same thing. And then I'm going to go back one more, right? And it's the exact same idea. I'm just replacing all these i's with I minus 1s. And in the example, right, this 2 to the I minus 1 is now 8. Plus that 1 is 9, minus 6 is 3. And so 6 is the team that 3 plays in the next round if the better teams win. And it's also the kind of 2 steps back in that chain. And then I'm going to make this new sequence B, which says, okay, for some AI, what is the alternate? Well, so it turns out that so the answer is like the alternate seed is not who 6 plays, right? So 6 is the previous primary seed. The team that they play is the new primary seed. But I want to go 2 steps back and figure out who they play in the bigger round game, and that's going to be the alternate seed, because those teams are always going to have the exact same matchups, just in a different order. If the better team, besides the team you're focusing on, always wins. So I'm going to go back 2 steps and figure out who that team plays in the bigger tournament, and that's what it is. And so to figure out who they play in the bigger tournament, I just take 2 to the I plus 1, that's the number of teams, plus 1, that's going to be the seed sum, and subtract out, again, that 8 of I minus 2, that's 2 steps back. In the example, again, that's 16 plus 1 minus 3 is 14. So 14 is the alternate seed in that specific example. And I want to know, what does b to the I over 2 to the I converge to? And so I'm just going to replace, all the stuff on the right. I'm going to divide everything by 2 to the I, right? So 2 to the I over 2 to the I is 1. 1, and I have 1 over 2 to the I minus I minus 2 over 2 to the I. So I have that. And I'm going to take a little step back and say, well, what is because we know what AI over 2 to the I converges to. So what is a to the I minus 2 over 2I converge to? Well, that's going to converge to, this really should be an arrow instead of an equal sign. This is going to converge to, that this one is equal. I'm just going to take 4 out of this 2 to the I and leave 2 to the I minus 2 and then divide by 4 to keep it separate. And now a to the I minus 2 over 2 to the I minus 2 is going to converge to the same thing as a to the I over 2 to the I, which is 2/3. So I have 2/3 over 4, which is just a sixth. So this term here, a to the I minus 2 over 2 to the I, is going to converge to 1/6. And what I'm left with is that b to the I over 2 to the I converges to 1. That should say, sorry, minus a 6. I'm not going to re-record this. Let's just say 1 minus a 6 is 5/6. And that's that is the fraction of the alternate seed. So the end of extra credit is we end up with 2/3, 5/6. So hopefully that was a fun puzzle for you to try and to walk through. So thanks for watching, and I will see you again next week.